Hello, sir.
I just got a little bit late here because of another meeting. Hold on. So we'll get started with the class. We are looking at the MATLAB codes, right? Yesterday. Okay, so let's get started. I'll share my screen. Allow to share screen. Okay. Do you see the program that we have in MATLAB?
Oh, yes, sir.
Yeah. Okay. So good. So this is this. I mean, we already looked at the explicit Euler method. Okay. Let's look at the implicit Euler method. Okay. So let's open implicit Euler. Okay. So all right. So what we have is this implicit Euler method is exactly the same as the before, except that I mean most of the code is the same, except that the yn plus 1 expression is different, right? So in explicit Euler, we had yn plus 1 is equal to yn times 1 minus lambda h, right? That means because this is 0.5y, we had minus 0.5h, right? That is the explicit Euler method. So the rest of the code is pretty much the same. So for example, if you see, I have h equals 1, number of time steps is 10, and then we are initializing to t, y and y exact to zeros. Then we are again solving the same problem, that is dy dt plus 0.5 y equal to 0, in which case you have f of y equals minus 0.5y. And then we are initializing the problem with y of 0 equals 1. And then we want to calculate either y of t equals 10 or 20. Okay. So that's what we're doing. So let me put it 20 here. Okay. And then we are initializing t to be 0, y of 0 equals 1, and then y exact is 1. And then we are looping over all of these things and incrementing the time and then calculating the solution. So in the implicit Euler, we have y of n plus 1 equals yn divided by 1 minus lambda h, right? In this case, 1 minus lambda h, lambda is minus 0.5. So as a result, what we have is 1 plus 0.5h. That's all is the change compared to the explicit Euler, okay? And then y exact remains to be the same. This is e to the power minus 0.5 t, okay? That is the same. So let us try to run this program. So again, we are using delta t of 1.0. Okay, let me run this and see. So it has printed some values, and then now you see this graph. Essentially, again, blue is coming from the implicit method, and then the red circles are from the exact solution. So there is some difference, but it kind of follows the exact solution pretty closely. Okay, this is for a time step of 1.0. Now let me put another time step. Let us say, let's make it 3.0 and then run it. Okay, so okay. What you see is that there is some difference, okay, but it seems to be yeah. So there are some deviations. You see that the red is now a little far compared to the blue and so on, but this is much better than what we had observed for explicit Euler yesterday, right? For example, for 3.0 yesterday, we already saw that there were oscillations, although the oscillations were converging, right, in the context of explicit Euler method. I mean, I can rerun this thing actually. The explicit Euler, okay, h equals 3, okay, and run this. Okay, you see that explicit Euler is already kind of showing oscillations, which is not correct. Whereas when we go to implicit Euler, it is still stable, even for a h of 3, it is still gives you, this kind of a nice solution, bounded solution. Let us try to put h equals maybe 4.2. Okay, so and see what will happen. So this is now above the stability limit prescribed by the explicit Euler method. Okay, but then as we know, implicit Euler is unconditionally stable. So as a result, this should produce a result, but that may not be accurate, but it still should be kind of bounded. It cannot be unbounded. So okay, so I think this seems to be good. Even with 4.2, you still get some good answer, right? It is not so bad. And I can even put in, maybe let us say instead of 4.2, I can put like 10 or something and see. Okay. Now you see there are, it has kind of not followed it properly. So there is a lot more difference, right? It should have decayed, but it is not decaying so much here. Okay. So there are things, but then you see that it has really not diverged, like in the case of explicit Euler method. So this is what we meant by implicit Euler is unconditionally stable, but it may not be. Let me put it to 10 to see the difference more clearly. So it may not be, the solution may not be accurate. Okay, that's what it kind of represents here, right? It is already very small, but this is still not gone to that level. Okay, so let me put even smaller and see. Okay, now I think you can clearly see that this is very small, but it has not decayed so much. But you see that you still get the answer. It is not giving you, oscillations or divergence and so sort of things. Okay. So that's about explicit Euler and implicit Euler for solving dy dt plus 0.5 y equal to 0. Now let us look at the one more thing, that is the trapezoidal method. Trapezoidal method is, we said, is another implicit method, but then is second order accurate. So the result trapezoidal method would produce is going to be better than the result implicit Euler would produce, because trapezoidal method is second order accurate and implicit and explicit are only first order accurate. Okay, so again we have pretty much the same code here, except for the line where yi plus 1 is calculated. As you recall, yn plus 1 equals yn times 1 plus lambda h by 2 divided by 1 minus lambda h by 2. And in this case, our lambda itself is minus 0.5. As a result, we got 1 minus 0.5 h by 2 in the numerator and 1 plus 0.5 h divided by 2 in the denominator. So rest of the code is the same. So I'm going to again run this for 20 steps and then see how the result is going to be. So it has run, and I think now you can clearly see the difference, right? So the blue lines are exactly on the circles, right? There is not even a bit of difference here. Okay, of course, there can be some in decimal places, but then you see that the second order accuracy of the method is demonstrated through this part of the code. Okay, so for example, if I go back and run the implicit Euler, you'll be able to see for h equals 1, we saw, we see a starking difference, that there is some difference, whereas that is not there in the context of, see, now there is, here you see that there is some difference, right? The red circles are not aligned with the blue one. There is some error, but then the moment you go to trapezoidal method, that is gone. Okay, so it is kind of second order accurate, so it gives you a much better answer. Okay, any questions so far on the explicit Euler, implicit Euler, and the trapezoidal codes and the what we have run? No? Okay, fine. So let us move on to the studying the problem for a purely imaginary right hand side. If you remember, we looked at lambda y prime equals I omega y, right? Where we said on the right hand side is purely imaginary, I omega y. That means it will produce oscillatory solutions. That's what we have looked at. So whatever we have learned in terms of that, for purely oscillatory, for purely imaginary lambda, explicit Euler was unstable, right? Whereas implicit Euler was stable and trapezoidal method was stable. That's what we have learned in the theory. So let us try to see whether that is correct or not through programming. So again, I have h equals 1, number of time steps equals 20. And then, but then here I have changed the problem. The problem is now dy dt. Instead of plus 0.5 y, I have I times 0.5 y equal to 0. So where I is the square root of minus 1, that is the complex number. That means your right hand side function f of y equals minus I times 0.5 y. Okay, that's what we have. Okay, so that is the right hand side. Oops, that is the right hand side. And then we are again given y of 0 equals 1, and then we have to calculate what is the solution. So I have used, so MATLAB supports the complex numbers. Both I and j are complex numbers. They're square root minus 1. Because I'm already using I here, I'm using j to represent the complex number. So this is the j. That means in an explicit method, we have yn plus 1 equals yn times 1 plus lambda h. Okay. But then here my lambda is minus I times 0.5. So this is going to be 1 minus j times 0.5 h is what I would get. Okay. So then y exact is there, which is basically e to the power minus j times 0.5 t. Okay. Here j is square root minus 1. So j is actually my I. Okay. Because I'm already having I used j of the MATLAB. Okay. Let us try solving this. So this is is with h equals 1. So this is basically for the stability limit. Actually, there is no stability limit because explicit Euler method is unconditionally unstable for all imaginary values of lambda, right? For purely imaginary values of lambda, it is not stable at all. So there is no delta t that you can take which will make it stable, right? Okay, but then we want to just try it out and see how does the solution look like. So I'm going to run this. Okay, so you can clearly see the red blocks, red circles are the exact solution. It is varying between +1 to -1. But then you can see the blue solution that is already diverging, right? You can see that its amplitude is increasing. That means if I'm going to run it for a little longer, instead of 20, if I put it 80, you will see that it will start diverging. It will grow larger and larger, and it's going to diverge. See, you can clearly see whereas the red ones are varying is in purely oscillatory solution. The blue one has diverged to 3000 to -3000. Okay, I think you can clearly see that. So that means it is not stable for any value of h, right? Even if I take h equals instead of 0, even if I take 1/10 of that, it is not going to be stable. Okay, so now I need to increase its value, make it maybe 400. Okay, now you can clearly see it is going from -1 to 1, whereas the blue one is started to show oscillations, and the magnitude of the oscillations are increasing, right? That means it's going to diverge eventually, whereas the exact solution is purely oscillatory. Okay, you get several problems like this in engineering and science. For example, the spring mass system is an example of an oscillatory solution. Oscillations of a pendulum, and then many other problems in vibrations, and even in fluid mechanics are oscillatory problems are there. Okay, so that is what we kind of take away from here, that explicit Euler is unconditionally unstable for purely imaginary right hand side, for purely imaginary lambda. Okay, fine. I think that kind of supports what we have learned. Let us look at the implicit Euler method. So implicit Euler method for purely imaginary right hand side. Okay, again I'm choosing h equals 1.0. Number of time steps is 20. Everything else is exactly the same. I should change this to I. Okay, because this is I, and then this is also I. Okay, and then we kind of do the same thing, except that now my yn plus 1 equals yn divided by 1 plus 1 minus lambda h. That's going to be 1 plus j times 0.5 h. And then this is the exact solution, which is the same as before. Okay, so this is now implicit Euler for purely imaginary right hand side. So let us run this and then see what it looks like. Okay, so as you can see, it is basically it is decaying. Okay, because of the diffusion that is there. Okay, we said it is only first order accurate, so it is decaying, but then it is not going to diverge, but it is not still following the exact pattern as such. Okay, so maybe I can try reducing the h and see if at all it's going to be better. So make it 0.1. Yeah. Did we say it is implicit Euler is unconditionally stable? Is unconditionally stable for purely imaginary lambda? I think we said, but it is only order. Okay, now you can see it is decaying because it's only first order accurate, but it is able to produce that oscillatory solution. But what we can also get from here is that there is a phase error that we have noted. So that means this peak will not be aligned with this peak at every after every cycle. That means if I run this for several more steps, we will see that it will not be aligned. That means let me make it little larger. Okay, and then run. Oh, I think this is now a problem. Okay, so it has decayed so much, but the other one is there. Okay, let me make it 0.5. So make it 100. Okay, it still has decayed, but then I think it is somewhat difficult to see the this one. Okay, let me put it back to 1. So, and then make it maybe 40. See, still works. Okay, it has decayed so much, but you can somewhat see that this peak is occurring slightly different from where this peak is. Okay, so you can see that it is not quite aligned, right? So there is a phase error. For example, you see this is where the bottom peak should be, but it is at a different location. Okay, so there is a phase error that is there, which is equal to omega cube h cube by 3. Okay, as we noted before. Okay. Then we looked at the trapezoidal method. In the trapezoidal method for purely imaginary right-hand sides, we noted that there is phase error, but there are no amplitude errors, right? There are no amplitude errors. It's going to be exactly, the same. So let's look at trapezoidal with right-hand side as imaginary number. So this is what I have. Again, I should change this to I. And then this is also I. Okay. So again, I have yn plus 1 equals yn times 1 minus j times 0.5 h by 2 divided by 1 plus j times 0.5 h by 2. Okay. So that is the only change I have to make. Oops. For trapezoidal method. So let's try running this thing. Okay. Now you see this is exactly on the correct solution, right? The numerical solution is exactly on the exact solution, but then you see that there is a small phase error, right? That is coming up, but then we know that this phase error is only 1/4 of what we noted in the implicit Euler case. So it will not be too much, but it will be there. For example, now let me run it for longer. Let me run it for longer. That means maybe let us run it for up to 80. Okay. Then we'll have several oscillations. Okay. You start seeing that the peak has moved out, right? There is this peak is red one peak is occurring somewhere else, but this is occurring somewhere else. But then you see that both of them are bounded between +1 and -1. That is because trapezoidal method has zero error in amplitude. It has only error in the phase, not in the amplitude, right? So as a result, you will get this behavior. But then if you can clearly see that there is a phase shift, there's a phase lag, which you can observe. If you kind of continue this even longer, you'll see that phase shift is there. I don't know. I'll just try. Okay, you see that there is a phase shift, right? It is kind of coming out of this peak. So this peak is occurring here, whereas the blue peak is here, and so on. Okay, so there is that error in the phase. Fine. So far, so good. So that finishes basically our all the three methods for purely real right-hand sides and purely imaginary right-hand sides. So this is consistent with what we noted in the theory in the lecture. Okay. Any questions so far on this? I hope this is useful. I'll share all these codes so that you can test them out and then run them and then understand it for yourself. And ideally, I should have maybe written just one program with a switch statement for explicit Euler, implicit Euler, trapezoidal, and then explicit imaginary, implicit imaginary, and trapezoidal imaginary. I did not do that. I just copy pasted the code and then wrote different programs. But then you are welcome to modify all these programs such that you can just write one program, maybe one for all the all the three methods for real right-hand sides, and then all three methods, one program for imaginary right-hand sides. Probably something like that you can do. Okay, that is going to simplify the programs. Okay, and consolidate them. Okay, any questions so far? Is this helpful? I hope this is going to be helpful for your understanding together with the lecture. Any questions, comments, anybody?
Sir, we can try with this all codes and let you know, sir.
Sorry?
We will try with all these codes, whatever your codes right now.
Sure. Yeah.
Yeah, then we will come to you, sir.
Yeah, sure. Okay, so I ended up making a few practice problems for you, which you can practice for the midterm exam. Okay, so I just thought I'll show you them and then I will share them with you through Code Office so that you can practice them. I think these will prepare you for the exam. I have given maybe some 5 problems. The first one is a matrix is given with a right-hand side B, that is 1, 0, 0. Okay, and then we are asked to solve the system, that is Ax equal to B. Solve the system Ax equal to B, where x equals x1, x2, x3. Okay, using LU decomposition, which you already know. So basically, decompose into L and U matrices, this 3x3 system, and then using 2 norm, calculate the condition number of the matrix A. Okay, and then comment on whether the matrix is well conditioned or ill conditioned. Okay, so I didn't provide the answer. Okay, but then you can check your solution x by multiplying it with a. Okay, so once you get x, you multiply with a, and you should get this b back. Okay, and then see whether you're getting the b vector or not. So you will get this correctly only if the condition number is kind of small. If the condition number is very large, your solution may not be very well behaved as such. Okay, so that you can check. So that is the first problem. You can perhaps practice this. Then let's look at the second problem. Second problem is consider the following tridiagonal matrix. So we are given a tridiagonal matrix. So there are 3's, -1's, and -1's on the above and below the diagonal. And with the right hand side vector given by 2, 1, 1, 2. Okay, so that is the right hand side vector that is given. And then solve the system Tx equal to b. So this T times x, x1, x2, x3, x4 equals 2, 1, 1, 2 is what you have to solve using the tridiagonal LU decomposition. If you remember, we have done the tridiagonal LU decomposition, which we also call it as the TDMA, right? Or we have also written the tridiagonal LU, right? Where we had above the diagonal A elements, below the diagonal B elements, and C, D along the diagonal, and so on, right? So using that, you solve and then verify your answer that you would get all ones for the solution. Okay, so when you calculate x values, it will be all ones. Okay, so that's another problem. Then third problem is calculate the one norm, infinity norm, and the Frobenius norm. Okay, and the corresponding condition numbers for the following matrix. You are given a simple 2 by 2 matrix system. You need to calculate all these norms. Okay, so I still calculate what is the norm in terms of 1, infinity, and Frobenius, and then calculate the condition number. Condition number is norm of the matrix multiplied by norm of the inverse of the matrix. Okay, so that you can easily calculate and then write them down. Okay, so those three problems are from the solution to system of linear equations. Then I put in a couple of more problems from the solution to system of nonlinear equations, in which case f of x is defined in the range of 0 to pi with with basically with this kind of arrangement, so essentially it's going from -4 to 4, where -4 to 0 it is -1, 0 to 2 it is x -1, 2 to 4 is 1. So you can easily draw how does this look like. And then so first problem is sketch the function f versus x. Then what is the appropriate method to be used to solve the root of the function f of x equal to 0. So out of the methods that we have learned, bisection method, Newton's method, or secant's method, and so on, after you sketch this thing, you will be able to realize what is a suitable method, or why out of these three a few methods cannot be applied. Only a particular method can only be applied. Why? I think that you'll be able to reason it out once you draw this sketch of this function. Then perform 5 iterations using that method and report the solution at the end of each iteration. Then you have to, once you selected the method, you will perform 5 iterations and then report the solution at the end of the 5 iterations. Okay, so that is the fourth question. Then the fifth question is we are given an initial guess, that is x0, y0 is given as 2.5 minus 2.5. We are asked to solve the system of equations given below by performing 3 iterations. Okay, so essentially this is system of nonlinear equations, right? X cube plus 3y square equals 35, x square plus 2y equals -2. Okay, so you need to solve this system with this initial guess, perform 3 iterations. So that means you're going to use the Newton's method, the general Newton's method.
So it will be Jacobian, sir, if I'm not wrong. We're defining Jacobian, right?
Yeah, you will use Jacobian and then calculate from there, right? We have done this thing. Yes. Okay, so I would suggest you practice all these. I think that will be a kind of good preparation for the midterm exam. Okay, any questions or any comments on this?
So it's very useful.
Sir, how many questions, sir, will be like? I'm sorry to ask this question, sir, but
no, in the exam.
Yes, sir. Yes, sir. Yes, sir.
Yeah. So in the exam, I'll probably put maybe 2 or 3 questions, not more than that. If it is somewhat involved, I'll put 2 questions. If it is okay, I'll put 3 questions. So exam will be for 1.5 hours, right?
Yes, sir.
Right, sir.
Yeah, 1.5 hours. I'll try to put it for about 1 hour. so that you have 30 minutes to, verify or correct and, do other things. Before you can verify, and if you have done a mistake, you can correct or something like that. Maybe I'll put 2 to 3 questions.
Right, sir.
Sure, sir. Thank you,
Okay.
sir.
Yeah.
Sir, one doubt
Yeah.
regarding exams. Sir, are we going to be asked for operation count and this pseudo code also, sir, or how it is?
No, pseudocode. So the thing is, okay, operation count I may ask because that is kind of part of the numerical thing. See, in terms of derivation, I may not ask you the same derivation that we have done in the class. But I may or may not ask, derivations as such. But then maybe at least the numerics you should be able to solve. Once you know the procedure, you should be able to solve the, numerical problems. Okay. So that's the thing. Derivation I may or may not ask because we have done it in the class. But if there is a deviation from what we have done in the class, let's say with a different starting point or a different procedure, then I may ask you to start with that and then derive the same thing. So that you should be able to do. But most likely it will be on numerical problems. Don't worry too much about derivations. Even if there are derivations, you'll be able to do them easily. Once you listen to the class. The other thing is that
Pseudocode.
Pseudocode also, if it is an algorithm, then you have to write pseudocode, but I will not ask you to write pseudocode. I think it's okay. If you know the algorithm, you'll be able to just solve it.
Right,
Okay.
sir.
Yeah,
Noted,
don't
sir.
worry about pseudocode. Pseudocode is primarily for you to help you to write the program, but not solve it as such. Okay. Yeah.
Thank you, sir. Thank you.
Yeah, no problem. But then
Yeah.
there may be some problems. For example, let us say, what is, for example, what is forward elimination, what is backward substitution, what is forward substitution, all those things. So there may be some problems where it may be a slightly different algorithm. May not be that we have learned. But I will highlight what is the new algorithm. So you should be able to follow these steps and then arrive at an answer. Okay. Something like that. Yeah. But I think you should be able to solve all these things easily, within the time frame. So I'll probably set 2 decent big, medium sized questions, or maybe 3 if one of them is going to be small. Okay. Yeah. Fine. Anything else? Anything else? Any other questions? Anybody?
Yeah, thank you so much, sir. Thank you so
No
much.
problem. No problem. Yeah. So 1 second. Yeah. So okay. So all right. So then let's get into the lecture. So let's start a new one. Start this. So I'll share these questions. You can work on them. And then I think that should be good. I don't have answers, but I think you should be able to easily verify your answers whether they are correct or not. Okay. And I should be able to easily do that. Okay. So with that, we are in the solution of ordinary differential equations. Okay. So we already looked at
Sir?
these 3 methods. Yeah.
I have a small doubt.
Yeah, sure.
Sir, in yesterday's class, we actually did not touch why trapezoidal actually captures the amplitude perfectly.
Oh,
We
is
only
it?
said
We
it
didn't-
is unconditionally stable, and then we went on to phase error.
Oh, we didn't do why the amplitude. Oh, we didn't do the amplitude part of it. Is it why the amplitude is?
Yes, sir.
There are no amplitude errors. That's what we have not done. Huh? Oh,
Yes,
so
sir.
there are no amplitude errors if it is purely imaginary. That's what we have not done. Okay. Trapezoidal method. Let me go back. Let me recall. So what did we write? We wrote something like a by b e to the power I times alpha minus beta, right? That's what we have written for sigma, right? For the trapezoidal method, wherein a was equal to 1 minus lambda, or it was 1 plus lambda r h by 2 whole square plus lambda I h by 2 whole square root. Is this correct? If somebody has taken notes, maybe they can verify. With the minus here, right? Because what we got yn plus 1 equals 1 plus lambda h by 2 by 1 minus lambda h by 2 times yn, right? That is what we got. So that means in the numerator we got plus, in the denominator we got minus, right? And then we said we're going to have, we're going to look at only real values of lambda which are less than 0, in which case in which case this is going to be smaller and this is going to be larger. That is why A by B is, less than 1. So that is why it is stable. Okay, so we said sigma is less than 1 because A by B is less than 1. But then this is the case for case for lambda are less than 0. But then now we want to look at purely imaginary lambda. That means we want to see y prime equals I omega y. Okay, so in this case lambda r equal to 0 and then lambda I equals omega y, right? That's what I have. So sorry, omega, it's just omega, right? So this is just omega. Then when lambda r equal to 0, what is A by B? So in this we know that A by B controls the amplitude, e to the power I alpha minus beta controls the phase, correct? So when lambda r equal to 0, what is A by B? Lambda r equal to 0, this is 0 and this is 0. So my numerator is 1 plus lambda I is omega. So this is 1 plus omega square h square by 2 square root divided by, this is also 1 plus omega square h square by 2 square root. So A by B is exactly equal to 1, right? So A by B is exactly equal to 1 for purely imaginary lambda. That means when lambda r equals 0 and then when lambda I equals some omega for purely imaginary lambda, A by B is exactly equal to, that means the amplitude errors are, the amplification factor is just 1. That means it's going to just keep that value. It is neither going to grow nor going to decay, right? It is neither that means it is a stable, right? It is what do you call such a thing? It's not unstable, it's not stable, it is kind of exactly will be equal to 1, right? So it is not less than 1. So that is the thing. That's why for purely imaginary lambda we have A by B equal to 1. That means your amplification factor equals to 1. That's why we observed in the program that it is neither growing nor decaying, right? Okay, is that clear? I think otherwise we have done the phase error is 1/4 of phase error obtained by implicit Euler, right? This we have done. Okay.
Yes, sir.
Yeah. Okay. Is it clear now, this part? I think I might have missed this to say this thing yesterday. Okay. Thank you for pointing this out. Okay. So till now we looked at the explicit Euler, implicit Euler and trapezoidal methods. These are of course kind of nice methods that people use, but there are another set of methods which are actually higher order methods. But unlike the Taylor series method, which we saw, which can be tailored to higher order schemes, these methods do not require or do not suffer from the same problems that the Taylor series method suffers from. And these methods are quite popular. They are known as the Runge-Kutta methods, okay, or RK methods. I think you must be familiar with these things. These are used quite extensively in the solution of PDEs or ODEs. These two names are German names, Runge and Kutta, so I may not be pronouncing them correctly. But in general, they're called RK methods. So RK methods are explicit methods that can be tailored for higher order accuracy. Okay, but then they do not suffer from the problems that the Taylor series method suffers from. So what are these problems that Taylor series method suffers from? We know that in the Taylor series method, we need to evaluate higher order derivatives, right? And we know that these higher order derivatives, the rho to the power n y by dou x to the power n, these may not be well behaved, right? They may not even exist. So that is the problem we have identified. Whereas what we do in RK methods is that between Tn and Tn plus 1, we're going to introduce, in between here, we're going to introduce more evaluation points. Okay. That means going from Tn to Tn plus 1 is 1 delta t. So within that delta t, we're going to introduce more points where we can evaluate the function. That is how we are going to increase the order of the accuracy. Okay, that is how we're going to increase the order of accuracy of the method. Now, it turns out by doing this way, it is not only the order of accuracy that is getting enhanced, it is also, these schemes also have better stability properties. Okay, they have better stability properties, which is a plus, right? Because if you have better stability properties, then you can take even larger h, larger delta t, and so on. Okay, so let us look at these RK methods, how they are constructed. So we're going to see the RK methods from by constructing a second order method, globally second order method, that is RK2. Later on, we're going to simply say that another method, that is RK4, exists, and which is fourth order accurate globally by understanding this particular derivation for RK2. So in general, in second order accurate methods, that is RK2, we will write yn plus 1 equals yn plus gamma 1 times k1 plus gamma 2 times k2, where k1 and k2 are functions. Okay, so they are functions, and gamma 1, gamma 2 are constants. Okay, gamma 1 and gamma 2 are constants to be determined. Okay, k1 and k2 are functions. So these are essentially functions that are based on the right hand side, whatever we get in the differential equation. Okay, so but what is the differential equation we want to solve? We want to solve y prime equals lambda y, or in general, we want to solve y prime equals f of tn comma yn, or f of ty, right? So we want to solve dy by dt, which is also as y prime equals f of t comma y. Okay, that's what we want to solve. Okay, so what are these k1 and k2? So the k1 is basically, k1 equals the step size h times f of tn yn. Okay, and then k2 equals h times f of tn plus alpha times h plus alpha times h. That is where you will evaluate this function, and then this is going to be yn plus beta times k1. Okay, I think this may be little confusing. Okay, so what we're doing is basically we have this function is evaluated tn and yn, and we obtain the new function which we call it as k1. Then the other function k2, we are evaluating h times f, the same right hand side function that we have, at a different time and at a different y location. Okay, instead of ty, we are evaluating at tn plus alpha h. You see here, we are not going to tn plus h. Tn plus h would have taken you to tn plus 1, right? We are only doing tn plus alpha h. Preferably alpha will be less than 1, so that we are not going to tn plus 1. And then you're also going to evaluate yn. So essentially the function you are evaluating at tn plus alpha h, and then some y value. That y value you are taking it as y1 plus k1 is this function, some beta times that k1. Okay, that's what you are evaluating. So at those 2 points of t and y, you are evaluating the function, and then that you are calling it as k2. Now, when you multiply that k2 with some gamma 2 and the k1 with some gamma 1, when you add it to yn, you're going to get the next yn plus 1. So that is the philosophy. Okay. So what we have done is essentially we evaluated the right hand side f of t comma y at different points. We know that if you evaluated tn yn and tn plus 1 yn plus 1 and then mix them with some h by 2, you know that it is trapezoidal method, but we are not getting there. What we are saying is that we are evaluating at tn yn and then some other value, that is tn plus alpha h, and then yn plus beta times some k1. Okay, so if you evaluate at this time and y values, that's what going to give you k2. And then when you take some linear combination of k1 and k2, that is when you add it to yn, you're going to get the next value of y. Okay, so that is the idea behind RK2 methods. Now, of course, it is up to us now to determine what is gamma 1, what is gamma 2, what is beta, what is alpha, right? Now there are 4 constants we have introduced in this process. We introduced alpha, beta, gamma 1 and gamma 2. These are values that need to be calculated. Okay. So that means now we want to calculate these values such that we are able to obtain highest possible order of accuracy for this method, right? So just like we have devised a highest order accurate derivative by using 3 points or 4 points or 2 points, we want to now do what is the highest order possible for this method if I'm going to determine these values. Okay, so that is the idea. Okay, so then let us write. So the right hand side is given here, f of t comma y. So let me write using Taylor series expansion. Taylor series expansion. Okay. Okay. Taylor series expansion for yn plus 1 can be written as yn, right, plus delta t, that is h times dou y by dou t at n plus h square by 2 factorial dou square y by dou t square at n plus h cube by 3 factorial dou cube y by dou t cube at n, and so on. Okay, so let me slightly write it differently so that it is easy for me. So we say h yn plus h times partial y by partial t. I'm going to write as y sub t comma n. Okay, that means this is dou y by dou t at n plus h square by 2 y ytt n and h cube by 6 ytt n. Okay, so that's what I have, plus and so on, right? Okay, so then, but we know that from the definition of the given problem, where y prime equals dy by dt equals f of t comma y, I know that dy dt, which is equal to yt, is f of t comma y, right? That means I can write for this yt at n as, that means I can write this yt at n as f of tn comma yn, right? Because the derivative value of the y is nothing but the function itself. So I can replace that. Now what about this quantity, that is dou square y by dou t square at n? So that means if I want to write dou square y by dou t square at n, I can write it as dou by dou t of dou y by dou t. That is nothing but dou by dou t of dou y by dou t is f of t comma y at n. Okay, so this is nothing but, because t, this is with respect to time, but then there are two variables t and y. T we can directly calculate, but then y is a function of time as well, right? So as a result, we can write this as dou f by dou t plus dou f by dou y times dou y by dou t, right? If that is the case, I can write this as ft plus dou f by dou y is fy times dou y by dou t is again f, right? Because we just wrote dou y by dou t equals f, that is given in the problem. That means this is equal to f sub t plus f times f sub y. Okay. Then if you were to evaluate at n, dou square y by dou t square, that is equal to at n is ytt comma n is nothing but f tn plus fn times fyn, right? So that is what we have. So I'm going to go back and then substitute for these two in here for ytn and yttn, and then write up to order h cube. So that means my Taylor series expansion for yn plus 1 equals yn plus h times fn plus h square by 2 times ftn plus fn times fyn, because I just substituted this one, plus order h cube. Okay, so this is my equation 1. Let's call it equation 1. Actually, there is nothing new we have done till now, right? I mean, this is basically the same Taylor series expansion, which we have used in the Taylor's method, right? This is exactly the same what we have used in Taylor's method. But then in Taylor's method, we said that you have to evaluate fn, ftn, fn, fyn, and so on, so that you get some kind of a second order accurate method, which we said is not well behaved. And many a times, this function, the function is not visible to the is not visible to the procedures that we're calculating. For example, the structure of the function, f of t is lambda n or lambda square y square plus some, alpha times t plus something. That structure of the function, we don't know many a times, right? When you write a program, this right-hand side is coming in a numerical way from some other subroutine, from some other procedure. So as a result, we only know how to calculate, how to evaluate the function, but we don't know its analytical form. So as a result, we won't be able to write the derivative of that inside a program. Okay, so because the structure of the function is many a times unknown in big programs, when you deal with FEM problems or CFD problems and so on, other vibration problems. So we cannot analytically differentiate it and then put it into the code. Okay, so that is the reasons. These are the reasons we said the Taylor's method is not super. That's why we want to move away from the Taylor's method and then do something else. Okay, so that's where these RK methods have found their place. Okay, so now let us go back. So this is the equation 1 we have. Then I have these two things we have proposed for the general RK method. Yn plus 1 equals Yn plus gamma 1 K1 plus gamma 2 K2. So K1 is already h times f of Tn Yn, but K2, you see, is about Tn plus alpha h and Yn plus beta K1. Now, eventually, I want to compare this equation Yn plus 1 obtained from the RK method with the Taylor method that we have, okay, so that I can determine these coefficients. So I want to equate that equation to this equation 1, but then we realize that this equation we have written is still in terms of K1, K2, which are themselves functions, okay. So I'm going to slightly expand them again here using Taylor series. So that means what we have written for RK method is Yn plus 1 equals Yn plus gamma 1 K1 plus gamma 2 K2. And then K1 itself is a function, some h times f of Tn Yn. And then K2 we have written as some h times f of Tn plus alpha h comma Yn plus beta times K1. Okay. Now, eventually I want to compare this equation 2, equation 1, so that I can calculate what is gamma 1, what is gamma 2, and so on. Okay. And what is alpha, what is beta. But then before I can do that, because everything in this equation are in terms of about n, right? They are in terms of either Tn or Yn. But in this equation, they are not about Tn, Yn, because they are in terms of Tn plus alpha h, Yn plus beta K1. So let me use Taylor series to expand K2. Okay, that means I can write this as, I can rewrite K2 to be equal to h times. So I'm expanding this entire function about f of Tn Yn. Okay, that means I'm going to write this as f of Tn comma Yn. So I'm using a 2D Taylor series expansion. Okay. When I say 2D, it is because we are expanding about Tn Yn. There are two variables. Okay, that means plus, now I have alpha h, that is the step, times f sub t comma n, okay, plus I have beta k1 times partial y t comma partial y is partial f with respect to y comma n, right? I have to take this derivative with respect to n, and then we may have second order terms, which are alpha h square by 2 factorial f pt comma n plus beta k1 square by 2 factorial f y comma n plus and so on. Okay, that is what we have. That means if I would write this thing, this is going to be h times f of, okay, so this is what we have. Okay, so this is what we have. K equals this quantity. But what is ft comma n? Ft comma n is ft comma n, so we don't have to worry. Okay, fy comma n is also we have. Okay, ftt, so we don't need to, so I don't want to include these terms because these are h square multiplied with h. That means it's going to be h cube. So I don't want to build a third order global system. I want to just build a second order accurate global system. So I'm going to only consider up to here. Okay, that means I can write my K2 as h times f plus alpha h times f of Tn plus beta K1 times f of Yn. Okay, plus and so on. Okay, so I have these two. Now I can go back and substitute into Yn plus 1 equation. Okay, so my Yn plus 1 equation is Yn plus gamma 1 times K1 plus gamma 2 times K2. That's going to give me Yn plus gamma 1 times K1 is h times f of t and yn, so f of n, plus gamma 2 is gamma 2 times k2 is fn plus alpha h f tn plus beta k1 f yn. Okay, that's what I have. That means I can write this as yn plus, if I collect fn terms, I have gamma 1 plus gamma 2 times h times fn plus I have this term is going to be gamma 2 times alpha times h square ft comma n plus I have gamma 2 beta h. What is k1? K1 is nothing but h times fn, right? K1 is nothing but h times fn, so I can substitute that. This is going to be h times fn, so this is fn times fyn. Okay, that's what I have done. So this is my yn plus 1 obtained from the RK2 method that we wanted to build. Now it's a matter of comparing this equation 2 with equation 1. Equation 1 is this one, okay? Equation 1 is this one. I don't know if I can copy this. Copy and paste. Oh, very nice. I will copy this. Okay, so I can move this. Oh, this is so convenient. Okay. So now I have, this is the equation 1. Okay, so this was equation 1, this is equation 2. Now I just want to compare these two. So if I say, that means we have order h term, order hfn. So this and this, I can compare the coefficients. So the coefficient here is gamma 1 plus gamma 2 equals 1. So I have first equation is gamma 1 plus gamma 2 equals 1. Then the second term is, what we have is h square ftn. So we have h square by 2 ftn. That means this coefficient, that is gamma 2 alpha equals 1 by 2, right? Gamma 2 alpha equals 1 by 2. Then the third term is h square fn fyn. H square is outside, fn fyn. So it means again, gamma 2 beta equals 1 by 2, right? So that means I have gamma 2 beta equals 1 by 2, okay? So I have 3 equations and 4 unknowns, right? My unknowns are alpha, beta, gamma 1 and gamma 2. So I need to solve for this somehow and then fix my value so that I can go back and design my third order accurate or second order accurate method, right? Which is not going beyond, so which is introducing basically more points between Tn and Tn plus 1. In fact, it is only introducing 1 point, right? Tn plus alpha h. Okay, we are out of time, so I'm going to stop here. Yeah, so I'm going to stop here. I hope you found it interesting, today's lecture. And then I'll post the practice problems so you can work on them, and the programs and the lecture. Okay, everything. And I'll see you guys tomorrow at 4 o'clock. Okay, we'll continue with this rest of the lecture on RK2 and proceed. Okay, any questions, any comments, anybody?
It's clear, sir.
Okay, fine. All right. Then I'll stop here, guys. I'll see you tomorrow at 4 o'clock. Thank you.
Thank you, sir.
Thank you, sir.
Thank you
Thank
very
you, sir.
much. Thank you.